Now, last time we had our last big idea. And what does that mean? Well, we're getting into Taylor series. And this is just a great way for us to take our function and do a great approximation for it. And so the idea is that we're going to create a polynomial, well actually a series, which we can think of like an infinite polynomial. And this is it, the sum, 0 to infinity, the kth derivative of the function, evaluated at a, times x minus a to the k over k factorial. And so what we're doing is we're trying to say, let's find something which is mimicking our function at x equals a. So that's what we're doing. We're saying, let's try to match the derivatives. That's what we mean by mimicking. So in terms of the series, we can't distinguish this function from this power series. And when I say this function f of x and this power series at x equals a are identical. Exactly identical. The function, its derivative, its first derivative, at the point. But here's where the power comes from. Because we do such a good job at matching at a, we can do a good job of matching near a, and near might be very flexible. Could be for all of the choices. So, right now there are 4 series that we know. And the first one, we didn't actually explicitly state this last time, but it is in fact a Taylor series. And that's the 1 over 1 minus z. And that is the sum from 0 to infinity of z to the k. And that's for any value of z which has size less than 1. And we call this our geometric sum. So really the geometric sum was our first sort of dip into the waters here of Taylor series. Now the other 3 which we did talk about last time is e to the z, and that's the sum from 0 to infinity of z to the k over k factorial, sine of z, that's the sum k equals 0 to infinity, minus 1 to the k, z to the 2k plus 1 over 2k plus 1 factorial, and cosine of z, sum k equals 0 to infinity, minus 1 to the k, z to the 2k over 2k factorial. Now in these last 3, they hold for all possible z. In other words, if I want to know what sine of 100 is, plug 100 into here and add up all those numbers. And if you do add them up, it will in fact give you the right answer. We didn't show it, but it's actually not so hard to show, and we will show later today that these do in fact converge. Now one of the things that you want to sort of get into the mindset of is to recognize, look, these are sort of forms. So that's why I'm not choosing to use the symbol x here, I'm choosing a different symbol, z. So what I should think of is I could say 1 over 1 minus something is equal to the sum of something to the kth power. So I can put whatever the appropriate something is there, and I just have to make sure I replace it by the corresponding appropriate something over there. And that's true for all of these. Again, these are just sort of our forms, our building blocks. So we want to get to the point where we're comfortable with our manipulation of our Taylor series. Now why do we want to do that? Well, it says it right here. It's a lot better and easier to adapt what you already have than try to come up with something entirely from scratch. That's sort of one of our goals. Our goal is not to keep doing a lot of work over and over and over and over, because that's a lot of work. Our goal is to say, here's some work, and now, in a lot of cases, we can save ourselves trouble by just using that same work again and again. So, what are some things we can do? Well, we've already said, look, we can change this inside function. So, for example, I can make this 1 over 1 minus x squared. Well, that would be the sum k equals 0 to infinity of x squared to the k, or x to the power 2k. You can take integrals and antiderivatives. That's how we got the Taylor series, for example, for arctangent, was we started manipulating the Taylor series for geometric by changing the inside function, by taking an integral, and now we got what we needed. We can start combining different power series together and Taylor series together. So for instance, I might have two pieces. I just have to put my pieces together. Now, if you do add things together, you have to make sure that the exponents agree and that the sums start at the same value. So, well, how do you do that? Well, if you want your exponents to agree, you can do what we call a shift. So, for example, the sum of akx to the k, if we start at n and go to infinity, is the same as the sum of a sub l plus q x to the l plus q if we shift starting out at n minus q to infinity. Now what's happened is we've shifted everything. And if you were to write down the first couple of terms, for example here you see the very first term would be a sub n x to the n. Over here, start with the index n minus q plus q is n, so a sub n x to the n. See, they actually match. We're just doing an appropriate substitution and shift. Now there's an important moral here, and once you get the hang of it, it's really a kind of a fun idea. It says, look, we're looking for a series, and there's only one. So if we find one series that matches with what we're looking for, it's the series that we're looking for. So that's very useful to keep in mind when doing some of the problems. We're going to be doing a lot of various problems over the course of the next few lectures, getting into applications. All right, so let's try things. All right, so let's try some of this manipulation. Find the Taylor series for f of x, which is x plus x cubed over 1 minus 2x. Now, when we're looking at this, one of the things we want to start by saying is, okay, what does this feel like to us? And here, if we pull up our series that we've talked about so far, we say, well, it's really closest to geometric. So we're going to be building off of geometric. It's not like the exponential, sine or cosine, because none of those functions are involved. There's really no way to manipulate this function to make it look like one of those. So our key building block is right there. Okay, so, let's think about this. What can we do? Well, let's start by talking a little bit about the exponent. Now, if you look at the exponent, you'll see the x plus x cubed. One thing that's true about the exponent is it's a polynomial. And polynomials are things that we like. You see, when we're working with series are like a huge polynomial. It's like a polynomial where we just took a couple more steps. Well, infinitely more steps. So, well, that's okay. So I'm going to think of this as x plus x cubed. And I'm going to think of this as 1 over 1 minus 2x. And I just noticed something. There was a small typo with this problem that we didn't even address. So we should come out and state it explicitly. When we talk about a Taylor series, we always need to talk about where we're centered. So a Taylor series is centered at a particular point. So the philosophy of Taylor series says I'm trying to mimic the function at a particular point. Sometimes you might hear of something called Maclaurin series. And Maclaurin series are Taylor series which are centered at 0. And generally, most of the time when we talk about Taylor series, that will be where we center, but it doesn't have to be. So, but we'll go ahead and center this one at x equals 0. Okay, all right. Back to our regularly scheduled program. Okay, so we have x plus x cubed times 1 over 1 minus 2x. This part, it's really a polynomial, which means we like it. Good. Now this part, well, this part's actually not so bad. You see, it feels the right form. 1 over 1 minus something. In other words, if you look at it, it's the right pattern for what we want for geometric. So that's also good news for us. That means we can work with this. So we're going to leave the first part alone. So that's x plus x cubed. And the second part, we say, all right, well, that's the sum from 0 to infinity of, now the something is the 2x. So 2x to the power k. All right, cool. So let's work with this. So that's x plus x cubed, and I'm not going to do very much here. That's the sum, k equals 0 to infinity, 2 to the k, x to the k. Now I want to keep going here. I don't, what's my goal? My goal is to get it down to a single series. I don't want to have any x terms times the series here. So I want to really sort of how bring it in. But I want to be careful how I do it, because the real goal at the end of the day is I really want to group things in essence by powers of k. So I want to have all the powers of k grouped together. So I'm going to do some distribution here. So I'm going to multiply through. So we'll have x times the sum from 0 to infinity of 2 to the k, x to the k, plus x cubed times the sum from 0 to infinity of 2 to the k, x to the k. All right, well that's good. Now what I can do here is I can multiply my powers of x on through the inside. When we do it here in the first term, what will we get? We'll get the sum from 0 to infinity of 2 to the k. Then there's k x's plus one more x. That means that there are k plus 1 x's. So x to the k plus 1. Plus sum from 0 to infinity, 2 to the k. Here, there's k x's. I'm bringing 3 more x's in. So there's k plus 3 x's, which means x to the power k plus 3. Now, one thing I could do at this point is we could say, well, look, can't we just rewrite this sum as sum 0 to infinity? And I can say 2 to the k times x to the k plus 1 plus x to the k plus 3. Is this true? And the answer is, it's true, but we aren't going to put it in this form. The reason we don't want to stay in this form here is because, again, we don't want to group it here because we want all the powers of x's that are the same power together. And what happens is that these are different powers of x's, and so it's not the right kind of format when we talk about a Taylor series. So it's not grouped by powers of x. So that's why we are not going to go in this route. So where will we go? Well, we want to get our powers of x the same. So we'd still like to put the sums together. The problem here is that in this first sum, our power of x is to the power k plus 1. And in the second sum, it's to k plus 3. And those are not compatible. So we got to find a way to make them compatible. So now is our sort of like we put on our thinking caps and say, what can we do? So what we're going to do is we're going to just do a shift. So this is getting into our shifting here. So we're going to do these separately. So here we go. On the first sum, we say, let's make this as x to the something. I want to make this look like x to the n. So how can I make it look like x to the n? Well, currently I have k plus 1, and I want to make that look like n. So in other words, instead of x to the power k plus 1, I'd have x to the power n. All right, so here we go. We would have, coming over here, so we're going to over to this side, a sum. Now let's think about what we have. When k equals 0, what does n equal? Well, it equals 1. All right. Now, here, this top number, this is actually, there's a k here. We oftentimes don't write it. So k equals 0 to k equals infinity. Well, as k goes to infinity, what does n go to? Well, it also goes to infinity. So that's not so surprising. They might say, haha, infinity plus 1. Yeah, still infinity. Now, we'll do the x to the n. That's the easy part. That's still x to the n. But how about here? So 2 to the power k. Well, what is k? I can solve for it. K is n minus 1. So I'll have 2 to the power n minus 1. All right, there we go. That's our first expression. Now, that's the first term. Plus, now we need to talk about our second term. So let's do our second term, and we're going to do that again. Similar process, but let's be careful here. Now, in our second piece, what do we want? Well, we want to have x to the n again. So here, we're going to do our shift a little bit differently. So we can shift the two terms in slightly different ways. And that's okay. It's totally cool. And we're shifting them in slightly different ways. But the thing is, at the end of the day, we're having it so that when we're done shifting, they look like each other. And so we'll do our little same idea here. K equals n minus 3. So what do we get? Well, we get the sum. And here, when k equals 0, what does n equal? 0 plus 3. So sum from 3 to infinity. 2 to the k becomes 2 to the n minus 3. And then we have x to the k plus 3 becomes x to the n. All right. Nice. Nice. Good. Good, good, good. So now, great news. In fact, fantastic news. Because one of our goals was, we said, look, we really want to get all the powers of n together. And we're getting closer. See, because that's x to the n, that's x to the n. They're now compatible. So we're like, perfect. Pull them together. Except, got to be a little careful here. Look at where we start. We start at different places. In one term, we start at 1. In the other, we start at 3. So, what can we do? So here is another thing you can do with sums, which is, let's pull off the first few terms. So in particular, we're going to pull off the terms for n equals 1 and 2. So if we do that, well, for n equals 1, we get 2 to the 1 minus 1, which is 2 to the 0, which is 1, times x to the 1. So that's x. Plus, and then we have 2 to the 2 minus 1, which is 2. And then that would be x to 2, so x squared. Plus, and then we have the sum from 3 to infinity, 2 to the n minus 1, x to the n. So this part here is this first sum. What we've done is we've said, hey, let's think of it as the first two pieces, then everything else. If you think about what we did back when we talked about factorials, it's kind of the same philosophy, right? So when we were doing factorials, what we did is we said, hey, pull off the first couple of terms as you need it, and then you have everything else. And oftentimes when we did that, we were able to simplify how we wrote things out. So the second sum, we're not going to do anything, but now what you see is our sums have the same start point. So by pulling terms off, we got to the same start point. They both look like x to the n. Oh, good news for us. Actually, fantastic news for us, because now we can put everything together. So what do we end up with? Well, we end up with x plus 2x squared plus the sum from 3 to infinity. And now it's one single sum. I'm going to just write this. Now both terms have x to the n, so it's 2 to the n minus 1 and 2 to the n minus 3. We could actually stop there, but I'll point out you can even go just a little bit further, because if you think about what this is, this first term here, that's 2 to the n times 2 to the minus 1, which is an over 2. The second term, 2 to the n minus 3, is really a 2 to the n over 2 to the 3, which is really an eighth. And so here, you can think of it as 2 to the n pulled out, and you get 1/2 plus 1/8, which is 2 to the n, and 1/2, that's 4/8, plus 1/8, which is 5/8. So we end up with, I'll put it up here in this corner. First term is x, 2x squared, plus the sum from 3 to infinity of 5/8 times 2 to the n, x to the n. And there you go. That's the answer. And so now that we have it in this form, we can actually start to do various manipulations. If we wanted to, we could, for example, say, well, what's the 10th derivative? Well, you look at it and say, what's the coefficient for x to the 10th? So here, if I wanted x to the 10th, I'd come to the sum and say, well, it's 5/8 times 2 to the 10th. And then you'd have to be a little bit careful. There'd be a 10 factorial floating around, but not too badly. If I wanted the derivative involving x squared, I say, oh, well, the power of 2 is here, outside of the sum, which is perfectly fine. This sometimes happens when you're dealing with series, where the first couple of terms are just a little bit different, but then once you get going after that, life is good and you can put it all together. So there you go. So this kind of demonstrates what's happening when we talk about shifting your indices. So we did a shift of index, and then you pull off some terms. This is some of the manipulation of sums that can be very useful when you want to understand what's going on. All right, let's do kind of a similar problem. Next example. Find the Taylor series for the following function. F of x equals x minus 1 times e to the x plus 1 over x. And we're going to center it at x equals 1. Now, if you go back to our list, you might think of, all right, I have a couple of things. Now, if we really think of our building blocks here, the x minus 1 we're fine with, that's polynomial. Polynomials are really just sort of like, oh yeah, no problem. We know how to deal with polynomials. Because series are polynomials. E to the x, well, all right, we're going to use something about e to the x. 1 over x looks like 1 over something, so we're going to use our geometric sum. So we're going to be using these two different pieces here. All right, well, now we have to figure out how to use them. So one of the things that's going on here is we're not going to be centered at 0, we're going to be centered at 1. What does that mean? It means that we want to write this in the following way, as f of x equals the sum from 0 to infinity, the kth derivative, excuse me, the kth derivative evaluated at 1 times x minus 1 to the k over k factorial. So in our final answer here, we really want to make sure we have x minus 1 to the k. That's actually going to be a good clue for us on how we proceed. So let's think about what we have. So remember our two rules that we're going to use. 1 over 1 minus z is equal to the sum from 0 to infinity of z to the k, and e to the z is equal to the sum from 0 to infinity of z to the k divided by k factorial. So here's the thing. Let's keep this in mind when we're thinking about how to do our manipulation. We want the part to the k power here to involve x minus 1, because I want to end up with things that look like x minus 1. So that's our mindset coming in here. So that says I need to make things look like x minus 1 showing up over here and x minus 1 showing up over there. So we're going to spend the first couple minutes here thinking about how can we work with the sum that we've been given to rewrite it in a more pleasing way. And in particular, our real goal here is to say, let's make it look like something that involves x minus 1. So the x minus 1 that we currently have in the front, that's actually great for us. Now, here we have e to the x. All right, we got to think, how can I make x look like x minus 1? Well, you're probably thinking the same thing I'm thinking. Well, just write x minus 1. But wait a second, that's not right, because that changes the function. Well, then add 1 right away. So if you do x minus 1 plus 1, you're safe. All right, plus 1 over, and again, I need to make that x look like x minus 1. So I'll make it look like x minus 1 plus 1. Again, I'm safe. I've made it look like 0. So let's spend some time here to think about what we have. So again, that x minus 1 at the start, we're okay with. E to the x minus 1 plus 1. I'm going to think of it again as that. Sorry, that's my x minus 1 plus 1. Now, if it was just e to the x minus 1, life would be great. But what do I do about that plus 1? Well, now we use properties of functions. See, that's the same as e to the x minus 1 times e to the 1. Ah, okay, all right, I see what I did there. You see, I used the fact that when I have addition up in the exponent, it becomes multiplication. See, what happens is this x minus 1 polynomial we're happy with. This e to the x minus 1, well, that's my e to the box, right? And the box, it's the right form, which means, again, I'm happy. And what about that e to the 1? Well, e to the 1, it's a constant. And that's essentially just a really simple polynomial. So now my pieces that I'm working with here, I'm happy with. That's the first part. Now, plus. All right. I want to make it look like this. So I say to myself, I have a 1 over, that's a good sign. And I'm going to put the 1 here, I'll put that in the front, because that's good. But now I say, whoa, 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 hold on a second. It looks like I have 1 plus x minus 1. I need a minus. Well, that's okay. Remember, in math, 2 wrongs make a right, which is to say 2 negatives make a plus. So I'll do a minus of x minus 1. Right? Because minus minus does make a plus. And so now, why are we happy? Well, if you look at it, the second thing, we now have it of the form 1 over 1 minus something, where our something in particular does involve x minus 1. Aha, good. We're ready to now use our tools. So what we've done is we're avoiding taking derivatives. For the most part, with one big exception, which we're going to do next time, we're not going to spend a lot of time doing Taylor series by taking derivatives. That's going to turn out to be a very inefficient way to do this. And instead what we're going to do is we're going to say, let's use existing Taylor series and manipulate them and then get that information to find our desired series. Okay, so let's come out here. In the first term, I'll go ahead and pull the e closer to the front. So e times x minus 1. And the e to the x minus 1, I now use my mold. So that becomes the sum from 0 to infinity of x minus 1 to the k over k factorial. Because my mold up here is x minus 1. So x minus 1 to the k over k factorial. Plus my second piece. So that's 1 over 1 minus something. 1 over 1 minus something is the sum from 0 to infinity of minus x minus 1 to the kth power. All right. Now we'll do a couple of hopefully not too bad manipulations here. The e to the power x minus 1 will multiply through. And what does that give us? Well, we get the sum from 0 to infinity. We get e times x minus 1 to the power k plus 1, because there were k of them here, plus 1 more. And that's divided by k factorial, plus the sum from 0 to infinity. And here, I'll think of this as minus 1 to the k, and then x minus 1 to the k. Now, we really want to get it into this format here, which means I really want to get one sum. Okay, so we're going to shoot for that. Now, this x minus 1 to the k, beautissimo, exactly the kind of sum we want. It's, spot on. Here, it's x minus 1 to the power k plus 1. Not quite right. So we need to do something here. So the something that we're going to do is do a shift. So on our first term, well, we'll let k plus 1 equal n, or if you like, we can say k equals n minus 1. So what we'll get from the first term is that this is the sum from, not from k, for n, that's supposed to be an n, equals 0, let's be careful here. K equals 0, n equals 1 to infinity. Then the e, well, that doesn't involve k at all, so that's still e. And then I get x minus 1 to the power n. And then for k, I get n minus 1 factorial. Plus, now here, I'm happy with this. So what I'm going to do is I'm going to do what I call just a change of names. So I'm going to replace the k by an n. And that's perfectly fine. You see, the k is an index variable. Sometimes I call it a dummy variable. It's just there to keep track of things. It's a name. And we can change names to be more convenient. That's what's happening when we do this. It's a similar thing that we do when we talk about doing substitution in calculus. We're just doing a name change to get something more convenient. Now you'll notice that here the starting indices don't match. This one starts at 1, this one starts at 0. So we say, all right, we're going to make this one start at 1, which means let's pull off the 0 term. So when I plug in n equals 0, I'll get minus 1 to the 0, which is 1, x minus 1 to the 0, which is 1. So I get 1 plus, now the rest of it is the sum starting from 1 to infinity, and they both have x minus 1 to the n. So I get the sum from 1 to infinity of e divided by n minus 1 factorial plus minus 1 to the n, and then that's times by x minus 1 to the nth power. And there we go. That's our Taylor series for the function f of x equals x minus 1 e to the x plus 1 over x centered at x equals 1. Again, this is a case where the first term is a little bit different. That's okay. That can happen. There's nothing wrong with that. It's okay to be a little bit different sometimes. It's, the diversity. It's a strength. It's not a weakness. So, all right, good. Good. Well, I think that's all we have to say about that one. Now, the important idea. Today's big idea. We should get to today's big idea eventually, right? And that's in the error approximation. So in essence, what's happening is we are trying to get an approximation to our function. So what we have is we have our nth term polynomial, and it's the polynomial where we stop at a certain point. So the series says never stop. No, this one says you stop. And so it's a sum from 0 to n. The kth derivative evaluated at a, x minus a to the k over k factorial. All right. Well, good. Now, question. This is approximating our function. Just like think of it like the tangent line. Because remember, the tangent line is a really simple case of a Taylor polynomial. The tangent line would be when n equals 1, the 1th order Taylor polynomial. Approximations are, of course, not exact. So there's going to be error. And whenever you're making an approximation, the real question is it a good approximation? So the way you answer that question is you say, well, how big is my error? So if you can say, look, I know that I'm off, but the amount I'm off by is very small, then you have a good approximation. On the other hand, if you say, I know that I'm off, and I have no idea how far I'm off by, that's a unknown approximation, which we usually interpret it as a bad approximation. So you do want to be able to say, hey, I have a good approximation. So how do you find it? Well, what you do is you say, look, the f of x, that's the actual value. The Pn of x, that's the estimate. And so when you take the difference between our actual versus our estimate, what you end up with is you end up with the error. So what we want to say is, how big is this error? That's our goal. How's the size? Now here's the really cool fact. Now the error, it turns out, this is always the case. So suppose I say, look, here's my number line, and whoops, let me see if I can fit my number line here. So here, this is A, this is the center, and I say I use my approximation to estimate it at x. So that's what I'm after. Well, it turns out that assuming your function is reasonably nice, which all the functions you're going to deal with are reasonably nice, in other words, you can take enough derivatives, there's going to be some point in between where the error looks like the n plus first derivative at that point c times x minus a to the n plus 1 over n plus 1 factorial. Now, if you look at this right here, and you say, it looks like our next term. And that's because it does look like our next term. It really looks like n plus first derivative, x minus a to the power n plus 1 over n plus 1 factorial. What's the difference? And here's the key. It's not at a, it's somewhere else, at some point c, where c is in between a and x. So, how do you get that? We're not going to go through the derivation, but something along the lines of lots of integration by parts. So let's just take it for now on faith. You can go look it up online, or if you really need something to do, you can open up your textbook. Oh, that's crazy. All right, so how do we use this? Well, we say, look, I just need to get an idea of the size. So I'm going to take the magnitude. And I can say, what's the worst case? So here, this part right here, it says, let's do some worst case analysis. So I could say, how can I make things as big as possible? Well, the n plus 1 factorial, there's really not much you can do there. And I'm thinking about x minus a to the power n plus 1. The largest I could make it is, just make it the size of x minus a to the power n plus 1. Here's the key. This is the part that could move around, the n plus first derivative at c. So what we can say is, well, let's look at the n plus first derivative, and let's look at what's happening between a and x. So in other words, we're going to say, look at the n plus first derivative in this whole range from a to x, and we're going to take the maximum. That's what's going to give us our worst case, is if we take the largest possible value for this first piece. That's why we know it's as large as it possibly can be. So, good news. When we ever test on this, and we have tested on this in the past, we always give you the formula, so you don't have to memorize the formula. What we want to do is make sure we understand how to use the formula. So let's walk our way through an example. So suppose I have the function f of x equals square root of 2 sine of x, and there's a 3-part problem, and hopefully we can squeeze it all in to what's here. So the first part, find p2 of x for the function centered at pi over 4. So that's the second order Taylor polynomial. That's what it means by p2 of x. So what does that mean? Well, so p2 of x in particular, that's going to be the function at pi over 4 plus f prime, the derivative of the function at pi over 4, times x minus pi over 4, plus the second derivative at pi over 4, times x minus pi over 4 squared, divided that by 2 factorial. And so yeah, be careful here. Sometimes you think, is it 2 or 2 factorial? The real test, for those who are, if you're paying attention or not, would be at the third one. So sometimes we'd go out and say, well, find P3. All right, so let's talk about our function. Well, here's our function. What is our f prime? Well, the derivative of square root of 2, sorry, I'm off this page there. Derivative of square root of 2 sine of x is square root of 2 cosine of x. What's f double prime? The derivative of square root of 2 cosine x is negative square root of 2 sine of x. All right, well, that's so far so good. Now, remember, we're not plugging in functions. We're plugging in functions that have been evaluated. So let's think about pi fourths. Sine of pi fourths. Sine of pi fourths is root 2 over 2. You're multiplying that by square root of 2. So if you take root 2 over 2 times square root of 2, what you're going to end up with is 1. Because you get 2 over 2. Now, f prime of pi fourths. Well, that's cosine of pi fourths, which is also root 2 over 2, times root 2, which means that this term is also 1. F double prime of pi fourths. Minus root 2 times root 2 over 2, which means that this term is minus 1. So our P2 of x, this is part A, is 1 plus x minus pi over 4, and then plus, should it be really a minus? Well, we'll write it as a minus 1/2 times x minus pi over 4 squared. And the half coming from the 2 factorial. Okay, so this is for part A. All right, good. Now, let's talk about part B. So, next question. For part B, what's the best possible m between 0 and pi halves? So let's think about what m is. So for m, we come over here. That's this m right here. And what you look at is, you look at the 2 plus 1th derivative. Because in other words, here, when you're looking for P2, you go up through the second order derivative. For your error, you say, what would happen if I went one more derivative? So in our case, if we went one more derivative, we would be in our third derivative. So if our second derivative is minus root 2 sine x, our third derivative, or I guess we could write it as f prime prime prime, is minus root 2 cosine of x. So what we want is we want m, that's how big can this function, minus root 2 cosine x, be for 0 less than or equal to x less than or equal to pi over 2. Now be careful. It doesn't mean, okay, look at the endpoints and see what happens. It says, well, where's the largest it could possibly be? And when in doubt, just make sure to make something as large as possible. So here, certainly the minus doesn't matter because we're taking absolute value. Root 2 is a constant, that's fine. And now we just say, okay, the only thing that can change depending upon x is the cosine of x. So what's the largest that cosine can get when I go from 0 to pi halves? Well, it's certainly not going to be at cosine of pi halves. Cosine of pi halves is 0, but cosine of 0 is 1. And it turns out the largest cosine can ever get, in terms of the size of it, is 1 in magnitude. And therefore, we get that the maximum value is root 2. And so that's our answer for B. All right, so that's how big our m can be. Worst case scenario. And remember, when we're looking for m, we're not saying, well, what's the truth? We're looking for, when we're saying m, we're saying, in the worst case, what could it possibly be? Because whenever you're looking for an error, you always say, well, what's the worst that could happen? And then let's go based off of that assumption. So now we're ready for part C. So give an upper bound for the error between f of x and p2 of x on the interval between 0 and pi halves. So the error is really saying, we're looking for our function f of x and p2 of x. That's really our magnitude of our n of x, which, according to our formula, and I can pretend I had it memorized, but secretly I'm just looking over here, that's m times x minus, now a is pi fourths, so, whoops, n should be 2 here, minus pi fourths squared, divide that by, and then, not square, Steve, you can do math, because n equals 2. 2 plus 1 is 3. Bloop, there we go. Ha. No one will ever know that I made that mistake. And downstairs, 2 plus 1 factorial, which is really 3 factorial. So, what do we get? Well, we know what m is. M is the max, so that's root 2. So that's equal to root 2. 3 factorial is, I'm going to move this up a little bit so we can see the bottom, 6. And then we get x minus pi over 4 cubed. Now, one thing we can say is this helps us for any particular value of x. Now, what if we just said worst case scenario? So between 0 and pi over 2, how big can x minus pi over 4 get? Well, the answer is the largest it could get is if I was at either 0 or at pi over 2. In both cases, I've moved out a distance of pi over 4. So this is certainly less than or equal to that constant root 2 over 6 times pi over 4 cubed. And okay, so that's root 2 pi cubed, divide that by 6 times 4 cubed, which is 6 times 4 cubed, right? Ha ha ha. You didn't think I'd know what the answer to that is. Ha ha. Well, you're right. I didn't know it was that 384. But, we all bluff when we need to. But anyways, this is, again, a worst case error estimate, which means it's not terribly far off. Now, can you do better? Of course, the answer is yes, by taking more terms. But for now, that's good enough for what we need. All right. So there you go. There's our upper bound, a numerical upper bound, single number. No matter where we go between 0 and pi halves, if we compare our answer from part A to our original function, we're never more than this far off. Most of the time, we're actually going to be a lot closer because the error is always about worst possible case, and we're almost never in the worst possible case. It's, how likely would that be to happen? Okay, so let's now use this error estimate. So the question here, we said, hey, you remember that nice series we had for e to the x? We claimed it holds for all values for x, but we didn't actually prove it. So let's go ahead and argue about why that must be true. So let's recall what our Taylor series is. So our Taylor series, that would be our sum from k equals 0 to infinity of x to the k over k factorial. Now, what we can do is we can use our idea of what we just talked about, and our idea is to say, let's look at our error, and what we want to show is that Rn of x is going to go to very small as n goes to infinity. Why does that help us? Well, what that says, in particular, it says, if I look at the nth order Taylor polynomial, so this is the series, So our polynomial Pn of x, that's the sum, k equals 0 to infinity of, not 0 to infinity, let's sum from 0 to n of x to the k over k factorial. So see, Pn of x says you stop at some finite location. You don't go all the way off to infinity. So what we can do is we can say, well, let's look at Pn of x versus e of x. They're going to be off for any particular value of x, and we say, well, as we add more terms, what happens to our error? If our error goes to 0, then that says that the Pn of x, which converges to this sum, is going to also converge to e of x. Okay, so that's our goal. So what do we need? Well, we need to recall what our error was. Well, that's all right. Let's just pull it back up here. So we're just going to refer to our little chart here. So our Rn of x, so that is our, we're going to take our m times x minus, in our case we're doing 0 because this is centered at x equals 0, to the power n plus 1, divide that by n plus 1 factorial. Okay, so this gives us an idea of how big our error can be. Now remember, how do you find m? Well, to find m, what we key off of here is we say, look, m, that's our max of our n plus 1th derivative of x. Now, here's where e to the x comes in really helpful. See, when you take the derivative of e to the x, derivative of e to the x, whoops, let me match what it says here. The n plus first derivative of t between 0 and a 0 and x. There we go. Sorry. Okay, so when we take the n plus first derivative of e to the x, the n plus first derivative of e to the x is e to the x. So what we really get is that this becomes the max of e to the t for t between 0 and x. Okay, so far so good. So now the question is, when is e to the t as large as possible? Well, it turns out you got to be a little bit careful here because there's two possibilities. So here's our center. Suppose I have x is over here. Then what do I have? Well, e to the x has this type of behavior. The maximum possible value will be to the far right. So it'll be at e to the x, because t will be somewhere in between 0 and x. So you might say, okay, that's it, e to the x, done. Well, but be careful, because we didn't say x had to be positive, x could have been negative. If I'm in this interval, where's the largest value? Well, again, it's still to the right, because we're increasing. So t is somewhere between 0 and x. So what do we get? Well, the max, it turns out, it's the maximum of the numbers 1 or e to the x. Whichever one is larger, that's what m is. Okay, but key idea, and this is important. In fact, you can tell it's important because I'm writing the word important. So that's how you know it's important. It does not depend on n. In other words, it doesn't matter which derivative I'm looking at. It still is the same thing. So our Rn of x, and I can't believe I did this again. I'm doing a bad job of copying. I should not be a copier. This should be less than or equal to, not equal to. So that's less than or equal to the max of 1 and e to the x. times the size of x to the power n plus 1 divided by n plus 1 factorial. And now the big question. The first part doesn't depend on n, and I want to ask the question, what happens as n goes to infinity? Okay, so that doesn't matter. In the second part, I have in the numerator, it's an exponential function, something to the nth power. In the denominator, I have n plus 1 factorial. If I have to run the race, and I do have to run this race, between exponential versus polynomial, what's going to happen? Who wins? The answer is, and we've done this before, the factorial wins. Goes to 0. So we're doing exponential versus factorial. I think I may have said polynomial a second, but I apologize if I did. Exponential versus factorial, factorial wins. There's a couple ways to convince yourself that this is true. One way you can think about it is in the top, at every stage I'm multiplying by something which is the size of x. In the bottom, I'm going to multiply by something which constantly is getting bigger and bigger. So if I go out long enough, say, where n is larger than, say, twice x, I'm going to start multiplying by huge numbers downstairs, and that's going to drive the whole thing to 0. So, what's our moral here? Well, our error is bounded above by something which goes to 0 as n goes to infinity. Well, that says that our error goes to 0. If your error goes to 0, that says there is no error. And therefore, we come to the conclusion that, lo and behold, that this sum is in fact equal to e to the x. And that's true for every value of x, irregardless of which x we choose. And that's why we say that this is an important series and that it works for all x. And this truly, truly is. When it comes to series, there are two important series. And all the rest are a distant second compared to the two. The first one is e to the x. You're going to see that again and again and again. And the other one is geometric. So if you're only going to learn two series, learn those two. All right. Well, that was e to the x. How about cosine and sine? Well, it's probably not going to surprise you. We're going to have the same sort of thought process. So we're just going to run through the idea. So again, same idea. So what do we want to do? Well, we're going to take a look at our error, Rn of x. It's bounded by m times size of x to the n plus 1 over n plus 1 factorial. Now, let's think about m. Well, regardless of whether I'm working with cosine or sine, our derivatives, they have one of the following four forms: cosine, sine, negative cosine, negative sine. Those are the four possible derivatives that we're going to see when we take derivatives of either the cosine function or the sine function. They alternate among these four. Not in this order, by the way. This is kind of a strange, erratic order. Ignore the order. But the point here is that I say, well, look, when I look at my derivatives, it's one of these four functions, and each one of these four functions, these are all bounded between -1 and +1. Well, that tells us that our m is less than or equal to 1. So we have that our error is of that form. All right, so m is at most 1. And now we say, aha! See, we come back here. It's again exponential on the top, factorial on the bottom. In this term we have this extra constant. Over here our constant's just 1. And definitely, same as before, which goes to 0 as n goes to infinity. Which means that regardless of which choice for x that we have, our error is going to get small in the long run. And therefore, life is good. Now, at this point, you're probably thinking, hey, well, what's wrong with, say, our geometric? You might say, shouldn't geometric also have something happen? and I just want to point something out for geometric. If I look at my function 1 over 1 minus x, if I look at the n plus 1th derivative, and we're going to do this a lot more next time, it's some constant c times 1 over 1 minus x to the power n plus. Let's see, what would it be? If I have, I guess n plus 1th derivative would be n plus 2. And if you're not careful here, the issue that comes into play is that this 1 minus x, there's an error that pops in. So you see, when you're centered at 0, at 1, it blows up. There's a blow up at 1. And because that there's a blow up, this basically says it's just too much, you can't recover from your problem. And that's why there's a limitation as to what happens here. So again, something really special is going on with e to the x and cosine of x and sine of x. In fact, something kind of magical happens. And I think we'll do that story next time. But that's it for today, and we'll wrap up for now. See you next time. All right, bye.